Hi there, welcome back to Topological for Geom Theory with Geometric Algebra. Okay, here's the episode 3 cartoon for today, but I decided not to do Lorentz transformations today. I'm going to do, what am I going to do? I'm going to continue doing what I did last time. But again, just to recap for early episodes, I'll just repeat some of the stuff. Here's a website where you can get some basic geometric algebra introductory material, plus a whole lot of philosophy, so it's kind of fun, I think. But if you just want to learn some geometric algebra, probably there are much better resources than my shorts and website. So it's just there for anyone who cares to look at it. The shorts that I'm going to do here are just topics that take my fancy every lunchtime. Not every lunchtime, but occasional lunchtimes. And not terribly pedagogical, but obviously just I'm going to be going in some sort of order of increasing sophistication, I hope. So what we were doing was checking the Pauli algebra. The matrix algebra has Pauli matrices, and you can define a very generic one using some coefficients A0, 1, 2, 3. And the proposal was that this maps onto a Clifford algebra in this fashion. There's a scalar, and then there are these bivectors here. And that's the idea. So one thing we did last time was check that the unit multiplication by the unit imaginary in the matrix algebra here corresponds to right or dextral multiplication by the space-time pseudoscalar times the bivector sigma 3. Okay, and remember these bivectors are also called relative vectors because they act like Pauli basis vectors. Okay, last time we checked the commutation relations, or at least in the first video. Then last time we checked the multiplication by the unit imaginary, and today we'll check the last relationship that I care to check, which is matrix multiplication. So here's the Pauli matrix, here's the Pauli spinor. We're proposing that it maps to right multiplication by the Pauli bivector times the wave function times the sigma 3 in the Clifford algebra. And just to remind you is that you could still be doing this in a matrix algebra of 4x4 matrices if you wanted to, real numbers. Remember, the complex numbers can always be lifted up in dimensions to a real 2n dimensional algebra if you want to do real numbers. So even in ordinary quantum mechanics, you really don't need complex numbers if you're prepared to use matrices everywhere. But this is a multi-vector algebra, so fundamentally different objects as far as computation goes. And this is the matrix algebra, but over the complex numbers. And it's the complex numbers that are a cause of so much rot because they obscure the geometry, is the way David Hestenes would say it. It obscures the geometry. So we want to work with real numbers and real geometry whenever possible. Okay, so today we're going to check in Python library GAlgebra, which I showed you how to install, very easy to install using PyPy. And if you're familiar with the Julia language, that's also pretty good. I think Chris Doran has a package called Simple GA. Well, there's also one called Multivectors, I think. I wrote a little bit about this on the T4GU website, but I'm not gonna look at these today. I'm gonna look at Python, and yeah, let's just go ahead and check it all works out. And apologies last time for using a clunky bash console. Today I'll upgrade to a Jupyter notebook for you. A little bit easier to read. Alright, let's stop the kernel here so that you get to see the code run live. Alright, so the first thing I'm going to import some packages. I don't think I need math today. In fact, I don't need any of the stuff here. I could just use GAlgebra and SymPy. Okay, but I'll use this stuff later on to do some Lorentz transformations, but not today. I'll just alias some names here for the matrix and the simplify for SymPy. I will be using real and imaginary parts. Remember, SymPy returns as real imaginary as a list, so I just pull out the first entry of the list for the real part, second for the imaginary. Then I need some symbols to use. I'll use SymPy symbols to define these. I don't need the A4 today, I guess. And then I need some symbols for my geometric algebra as well to define some basis vectors. And here I define the geometric algebra in this expression here. The metric is east coast plus 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 minus. And here I alias the basis vectors, orthonormal basis vectors, anti-commuting, anti-commuting, anti-symmetric, sorry. Or the product's anti-symmetric. And the pseudoscalar is this thing here. You can take your algebra object and use the capital I function to get a pseudoscalar, but I just alias it to IPS for I pseudoscalar. And then these are the Pauli bivectors, sigma 1, sigma 2, sigma 3. And because these E's are orthogonal, in GeoGebra, the asterisk operator is the geometric product. And so that'll also be the same as the wedge product because they're orthogonal. Okay, to do these checks, I firstly need to define the Pauli spinner, which is two-component spinner here. First row is A0 plus IA3. Second row negative A2 plus IA1. The negative is just by convention for mapping onto the geometric algebra with a plus sign right here instead of a minus sign. And so this is the multi-vector version of this, and we're proposing that these two are the same. So the first check that we did last time was the multiplication by the unit imaginary, and that was the same as right multiplication by the pseudoscalar times the sigma 3 matrix. Okay, so we did that last time. This time I'm going to check multiplication by the actual Pauli matrices. So here's the Pauli matrices P1, P2, P3. You check that hopefully I've got the signs and the entries correct here. So this is really I should do it so the rows are clear. Row 1, row 2, row 1, 2. Yeah. Here I just do one of the checks for the commutation relationships, but you can do the others if you want. But here's the main thing that I wanted to do today, right at the bottom here. I want to check that the multivector corresponds to the spinner. The multivector MV corresponds to the spinner. And I could use some tolerance, but I realized that I'll have to put an absolute value sign around that, and I probably could do that. Actually, why not? Maybe let's try it. So the problem here is that if I use an equals comparison operator, it won't work if it's trying to compare an EX-EY with an expression that goes 1.0 times EX-EY. So SIMPy, or the overload for the comparison for SIMPy, will will say that these are not the same. So in fact, that's not equal. That'll be true, and that'll be false, even though we know it should be true. So to get around that, I have to just respect floating point numbers here, and so I take a minus sign, take a difference of these things, and then algebraically simplify it to get rid of, square roots and things like that, and then hopefully the expression will be 0 if the things are in agreement. But let's leave this one with the absolute value in here. Hopefully that'll work. Python's usually pretty good at that. So let's run this code. It didn't work. Oh, SIMPy is not defined. Oh, yeah, maybe I didn't run this code here. Yeah, there we go. Good. Okay, so let's quickly look at this code. So the scalar part of the multivector, that's this bit here, should be the real part of the first row of the spinner. The E1, E2 blade or bivector part of the multivector should be the imaginary part of the first row of the spinner. And this is the interesting bit. The E1 or EX times EZ bivector part of the multivector should have the negative A, so that'll be this this bit here, negative A2. So you might think that you need a minus sign on this, but in fact it works out fine without the minus sign. In fact, you'd need the minus sign if it was E3, E1, I think. But I'll show you that GeoGebra doesn't like that. It doesn't use these things in cyclic order, which I think is a bug, really. But let's have a look at it. So in fact, I've got a multivector already defined. So if I do blade coefficients on it, and I try the E3 times E1, you'll see it doesn't work. Okay. If I run that, I get an error. it's got a negative sign, so it interpreted E3 E1 as a negative. So it's doing some sort of negative thing here. So it's the order of it isn't cyclic. I think the cyclic order should be EZ EX. So that's a problem. So what you have to do is respect the order that the GAlgebra uses, and then you get the correct coefficient A3. And of course, it returns a list. So if you want to extract the entry in the list, you have to index it. Now that'll pick up the negative sign on the A2. So we don't, in fact, need the negative sign in front of that. That'll be correct as is, and so we can just use it like that. And the other one is just normal. The E2, E3 component should be the imaginary part of the second row of the spinner. And so let's do the checks. It looks like I previously ran this code and it worked out all right, but let's do it live. So Pauli matrix P1 should map to the multivector sigma 1 times the wave function times sigma 3. Let's check that. Yeah, it works out true. And I just do the two others. Pauli matrix 2, Pauli matrix 3. You could probably package this all up in a loop. Okay, that's all I wanted to do today. Just shows you how to use some really nice and simple Python, which almost is like just writing the algebra out, as if you were just writing it out by hand almost. That's the really nice thing about Python. Let's have a look at what to do next. So yeah, so maybe next short I'll do Lorentz rotations, just to show you that they really are just simple rotations. You can boost some coordinates by a rotor. So, and it's exactly the same expression for rotations in space. Works for space-time without any change. You just do the same thing. Sandwich product of a rotor and the reverse rotor. And then maybe later on, I think I want to do some linear algebra. So let me just tease you a little bit with this. The reason, of course, you want to do linear algebra is so much quantum mechanics is based on linear algebra, but also the beginnings of gravity, general relativity, thought of as a gauge of the geometry. So like a gauge theory of gravity, where you've got you imagine a flat space-time, and instead of curvature, you can just do geometric gauging. So it's not like a graviton or fundamental particle, but kind of in a way it is. So it's a different way of doing general relativity, and it uses a lot of linear algebra. And the great thing about it with geometric algebra is, well, what is linear algebra? It's algebra of linear vector spaces, basically, and that is geometric. And so linear algebra is really a subset of geometric algebra. But doing your linear algebra without matrices, but with general geometric algebra concepts, means that you don't have to do enormous matrices if you want to go up into higher dimensions. Not that we will, but we'll stick to 4 dimensions. But just a whole lot of other expressions, just much more, I don't know, you hesitate to use the word, but I think it's correct to use the word beautiful. In geometric algebra, just everything just is so nice, and you get much better geometric insights as well. So maybe some shorts later going into next year as well. I might be looking at some linear algebra, hopefully. Linear functions and things like that, determinants, and figure out what the trace means and stuff like that. Okay, but that's all I've got for you today. Next time, we'll do some Lorentz transformations. Okay, bye for now.